I will quickly introduce the object detection. It's a field that changing very fast, as you know. So my video is sorry, I don't have time to update right now, but I will update later. But still, it's very useful. So let's look at what is object detection. So let's quickly review the popular computer vision tasks. So first is called classification, right? The most basic one is try to classify an image. If the image is a cat, dog, or person, so it's called classification. Classification implies that there's only single object in the image. Okay, so it's assumed there's only single image, and they don't know, and the image, the object is usually in the center of the image, or that's classification. So usually we want to know more details about the object, so you can do one step further to localize it. However, it's still assumed that there are only one object in the image, so the application is a little bit limited. So if we want to find the multiple objects in an image, we need to do object detection. Object detection will use a box. It's called bounding box to locate the object. So here is the example. There are three objects, three dogs, or two dogs, one cat in the image. Object detection will find them all, dog, dog, cat. But the bounding box is not easy to describe the changeable object. It's only good for rigid objects. So if we use a bounding box to find a dog, you can see that the box includes a tail and a lot of background inside the bounding box. So the better way is to find the contour, the edge of the dog. It's called segmentation. So segmentation will try to find all the boundary of an object, all the boundaries of all the objects inside the image. So it's called segmentation. There are two kinds of segmentation. One is semantic segmentation. Semantic segmentation will try to separate the background, or like a grass, right, sky, trees, and the case, or it's called semantic segmentation. Another one is do object detection first and do segmentation. It's called instant segmentation, which is focused on the objects, or foreground objects. So here's the example of object detection in a picture. Previously, it's called previously you call it the background subtraction, or try to detect background, subtract the background and find objects. And that's a old trick. Now we do object detection. So here's a wonderful video made by the YOLO V2 author. We skip that. So as we know, there's a benchmark. The most popular data set is called Coco. Coco has labeled a lot of objects, and it's become a benchmark. It's good for segmentation and object detection. So we can see the winner are original. The winner was the mask RCNN, mask RCNN, and the YOLO version. But YOLO is famous for fast, not for accuracy. So for accuracy, usually we would say the region proposal method has better accuracy. But mostly we will use YOLO. I assume that you have heard YOLO before. So here is the brief history of object detection. Originally, the best model was called deformable part model before deep learning was popular. So it's a shallow learning model. And then the first version tried to combine traditional method with deep learning. It's called the fast CNN, right? CNN is a convolutional neural network. And then it's keep improved. So it has three versions, faster. It has RCNN, fast RCNN, and the faster RCNN. And then YOLO is called you only look once. We try to use one neural network to predict both the bounding box and the classification. That's why it's called you only look once. And it becomes a very successful architecture. architecture include a single shot money box detector is included in the TensorFlow Lite. And then the RCNN improved version for both segmentation and object detection. And the YOLO V4, V5, now we have 6, 7, 8, and also YOLO 10. Today I'm only cover until YOLO V5. So before we continue, how can we detect an object? Previously, people try to detect a location where there may include object, how it's called objectness. How likely this image page is an object. So traditionally, people will try to group the pixel that has similar look similar appearance, and the group name is a big pixel. It's called a super pixel. And then we'll try to group those super pixel. To group those pixels, we will have a lot of box, right? A lot of bounding box candidate. And then you can try to combine those box or to find the objects. Okay, to combine the overlap box. And then finally, if you are lucky enough, if you are lucky enough, you will find the objects. It was called a selective search object. So to find the object, we need to do a zigzag scanning. It's called sliding window scan because the object can be anywhere in an image, right? It can be far away or very close, can be large or small. So we need to do scan all possible locations. It's called sliding window. So the first step is to find all the regions that could maybe have the objects or could have the objects. It's called region proposal. Okay, so traditionally people are training region proposal selective search detector. And then after 2012, Hinton has proposed the AlexNet. Hinton and his students. The researcher tried to combine deep learning with selective search. So the first version of RCNA is to combine the region proposal with convolution neural network. It's first we will try to extract all regions that could have objects or object candidates. It's around 2,000 proposals, 2,000 region proposals. All right, you can see that. And for each proposal, they will calculate the CNN features and then try to classify into one of the objects. So this is the first version RCNN. As you can expect, it's very slow. It means that you need to do CNN classification 2,000 times. Okay, for each region proposal, it will apply the convolution neural network and will predict the two variables. One is the size of the location of the bounding box. It will predict the location of the XY location and the width and height of the bounding box. It's a regression problem because your bounding box will try to match the original object. And the second task will try to classify the object into one of the categories or to recognize the object. So each neural network will do two things: regression and the classification. So RCN is very slow. You need to do CNN classification around 2,000 times. The first version takes around 1 minute, 47 seconds to test on NVIDIA K40. And also selective search is a traditional algorithm, a fixed algorithm using shallow architecture. So second, they try to speed up the RCN. Its second version is called fast RCN. So instead of running CNN 2,000 times, why not we extract the CNN features of the whole image once? So it will run just once per image, and then we will try to apply the region proposal on the same feature map. Or we will apply the regions of interest RI on different part of the image, and then the same predict the bounding box, regressor, and the classification, soft maze classification. The third version is to replace the selective search with neural networks. So now they have a region proposal network, which is more accurate and easy to speed up on GPU. So it's based on CNN. So the architecture of based on CNN is that first extract the CNN features, apply the CNN architecture, and then there now is one branch for additional network called region proposal network. It will propose the regions, and then they will apply the region of the on the feature maps, and then do classification and the bounding box regression. So here's the speed improvement of the shorter the better. So the faster RCA is only 0.2 second on K40. So it's approach real time. Usually real time means 30 frames per second, 30 frames per second. So it's not real time, but it's close. So summary of the RCN trilogy for your reference. Okay, so now we are ready to introduce the most important architecture for object detection. You only look once, YOLO. So first, the YOLO want to reduce the number of proposed regions, right? Because the region proposal is 2,000 bounding box. That candidates, that's too much, too many. That's too many. So how can we do that? How can we do that? Let's look at the picture. So YOLO first divide the regions into S by S regions. Here, this example is divide the image into 7 by 7 regions. And for each region, it will only predict one class and the 2 bounding box. So that's it. It will force divide the image into multiple grids or into grids. And it's focused on speed. So it will sacrifice the accuracy of very small objects, but he thinks it's okay because usually the application we want to identify the objects close to us. Right, so he divides the image into a S by S grid. Each grid predicts B bounding box. Here B is 2 in the YOLO V1 and C plus probability. For each bounding box, we will have a bounding box vector or the upper left corner or the center of the bounding box. Depends on the different formats. The XY position of the center point and the width and height of the bounding box. Also, there's a confidence score. It's possible that your bounding box does not have an object, right? So the final prediction will be S by S by B multiplied by 5, or this is the vector size, or the final vector dimension plus the number of classes. Let me go back to this picture. So for each grid, we will predict 2 bounding box. And each grid will only have 1 class. So the color is the class. We'll say the purple is the bicycle, green is the door. Yellow is orange is the car, and the blue is blah blah blah. So, and it will combine with the bounding box. Separate the bounding box. Combine smaller boundings with the larger bounding box with higher confidence score. And finally, by combining the grids, you will have a good bounding box. Okay, so we know based on those information, we can calculate the dimension size. Here's the architecture of YOLO V1. So you only look at once, you only have a CNN, only one CNN, right? And this CNN architecture will produce 30 7 by 7 vector. Each represent one grid, and the bounding box 2 multiplied by 5. Each bounding box has 5 dimension. So size is 5, or 2 times 5 plus 20 plus is 30. So the final tensor dimension is 7 by 7 by 30. Okay, so YOLO is very fast and accurate enough, but it sacrifices the accuracy of very small objects. And also, it's not possible to detect the 2 objects in one grid. Okay, So here's an example of detect YOLO. So suppose we have three class. It's the same as just a concrete example. So each grid, suppose we have 3 by 3 grid. Each grid will predict one bounding box, and the bounding box need to 4 variables define the position, the x, y, location, and the width and height. Also, you need to give a confidence score. So for the first 3 grids, there's no object, so the confidence score is 0, and then it doesn't matter what value we can put random value because there's no objects. And for the middle grid, there is one object. And the class is second class, so class is one hot encoding, right? Okay, so the 2 green and the yellow, they are bounding bars of cars. Okay, so here's the YOLO detection flow. First is divide into grids 3 by 3, and each has 2 bounding boxes. And then we remove the bounding box with lower confidence score, and there are 4 left. And then we try to do non-max separation. We will left the bounding box with max size and larger size and high confidence score, right? And then remove the other. So let's go non-max separation. Remove the non-max bounding box. To evaluate the performance of an object detector, we do intersection over union. So we first need to calculate the intersection area of the ground truth, the correct bounding box with the predicted bounding box, and then divide by the overall size of the 2 bounding box. It's called the intersection over union. So actually we can quickly calculate whether 2 bounding boxes are intersect or not. We just check their corner position, their corner locations. So just suppose if they have overlap, and then all the max value should be positive, right? Or should be positive. Otherwise, they are not overlap. Or they are not. Okay, so to be overlapped, the yeah, the right corner, upper right corner of the red box should be larger. X should be larger than the upper left corner of the blue box. So you can check it. So you can quickly compare the locations and find if they are intersect. Okay, so now maxima separation. How is now maxima separation is to combine multiple bounding box. Discard all box that we've covered as a score less or equal to 0.6 or less than a threshold, and pick the bounding box with the largest confidence output. So to make detection very fast, the original authors has proposed architecture called darknet. They implement in C++. So the darknet use both 33 by 3 filters and to extract feature, and they use 1 by 1 filter, right? We have introduced 1 by 1 filter is used to reduce the output channels. Okay, but the modern architecture has implemented in PyTorch. The darknet was caused some problem of integration with Python framework. So here's some performance results on NVIDIA Titan X. You can see that the YOLO, you can easily adjust the speed trade-off between speed and the accuracy. For example, you can use a convolution layer has less layer or 9 convolution layer, or you can use less grids. So the faster version can run 155 frames per second on NVIDIA Titan X. That's extremely fast. In the meantime, the faster CNN can only run like 18 FPS. So YOLO is very fast. Of course, they have some drawbacks also. First is that is less accurate, has lower recall rate because it's used grid. And each grid can only find one object. So it's difficult to detect small objects. To address those issues, the author proposed a new method called anchor box, and also for version 2 they try to include new training techniques. So anchor box was the key point of YOLO V2. However, in YOLO V, starting from YOLO V7, they remove anchor box. Okay, so I don't know whether I should introduce anchor box or not. But let's quickly get the idea. So suppose we original YOLO V1 can only predict one object in one grid, right? So if the object are overlapped with other objects, you cannot detect two objects. The idea is uh, to have multiple bugs in one grid, right? To have multiple bugs in one grid. So the size of bugs was defined by this learn unsupervised from the training data set. The authors run k-means. So they find that as many human pedestrians will have a rectangle, right? The vertical rectangle. However, the car will be a horizontal rectangle. So they will design different bounding box, anchor box, and each grid can have multiple anchor box. So that's the idea. Also, if you want to detect small objects, you just add a lot of small anchor box. So now each grid has multiple anchor box, which each anchor box has its own class. And the bounding box location, cover the score, and each bounding box can have each anchor box can have different class. That's the key. So now the final feature map size is the number of bounding box multiplied by the 5 plus the 100 plus number. Plus number. So they also use k-means to find the anchor box. They find that 5 anchor box is the best on Coco dataset. Depends on your application. And now the bounding box position is relative to the grid. Relative to the grid. You can watch the video. But anchor box has been removed since YOLO V7. So it's less important. It's hard to label and track. So another feature of YOLO is try to detect as many classes as possible. So they try a hierarchical classification. Also, yeah, you can. It's very similar to how human define the ontology of animals or plants. You first classify whether your objects belong to animal, artifact, or natural object, and then do further classification. So trying a hierarchical classification. So YOLO V2 is more accurate, still very fast. And the V3 is the incremental improvement to detect objects at different size. Also include the feature pyramid with 3 scales and more cluster, more anchor box, and the fixed sum box. So there's a technical report. V3 is a technical report. After version 3, the original author gave up. He announced to quit the computer vision because the detector has been abused. Or the object detection has been used to locate people for commercials or for military object detection. So he decided to quit. After he quit, the people still continue improving YOLO architecture. So as I said, object can be far away or very close, can be very small or large. So we need to detect objects at multiple scale. However, the neural network convolutional neural network is naturally a multi-scale architecture, like a pyramid, because we do max pooling. We do max pooling every time. Every time we do max pooling, the original feature map becomes 1/4 of original size, right? So if we want to detect the object at different scales, we can just detect the features from multiple of each layer of the convolution. So we will have multiple bounding box detection, and we can detect object at different size. So that's a idea of SSD, single shot multi-box. So each feature map, each layer, they will try to predict the class feature detection. Okay, but YOLO, you only predict the final class, the V1, will do 98 per class. Okay, so it's V1 has 98 bounding box, right? 7 times 7 times 2, each grid has 2 bounding box. It's as 8,732 bounding box class. So how can we detect the object at different scale? We can do something like this, feature pyramid. We can, downsize the feature each layer and try to predict. Prediction on a smaller feature map means detect large object. How to, yeah. So it's a very common trick, feature pyramid. And as I said before, convolution neural network create a feature pyramid naturally, right? Because we do max pooling. So, but the final layer has very little details because it's been filtered out, right? But more semantic value. So the SSD originally tried to predict at each layer of the CNN single feature map, and the YOLO is a single feature map to predict on top of the feature map. But we can improve the accuracy, right? By combine the feature, scale up, and combine the feature with early layers, so that we will have more details, more object details. So that's the feature pyramid network. It's a slow but accurate. So it's try to scale up, dump small feature map, and add back to the previous layer. So that you can keep the semantic value and also keep some details of your objects. So it's an improved version of based on faster RCNN, but it has additional feature pyramids for prediction. Slow but accurate. And the authors, part of authors are from the RCNN team, and the Kai-Ming He, author of ResNet, predict the retina net. So the innovation is to have the feature pyramid net, additional feature pyramid. And he proposed focal loss can focus on the less common classes. Okay, so basically other architecture is between the backbone and the neck. We will continue to introduce the object detection next week. Thank you for joining today's class. See you next week.